Hello again. The goal of this video is to discuss what's called partial fraction decomposition. So basically, by the end of this video, you should be able to decompose, which means to break apart, a rational expression into a sum or difference of smaller rational expressions, or maybe not smaller, but different ones. Okay, so before we go ahead and decompose rational expressions, I want you to remember what you know about just working with rational expressions in general. So I want you to try simplifying this on your own, and I'll come back with the answer. Okay, so you should have tried that on your own, but you can check your work with mine. I'm not going to go into detail because this is background knowledge. But basically, you need to get a common denominator, combine like terms, and you should get 4x minus 13 over 2x squared plus x minus 6. Go back and check through my work if you have any different numbers, and come with questions if you are not sure how to do this. Okay, so this is what we already learned in previous chapters, working with rational expressions. We can combine them, add, subtract, multiply, divide, whatever it may be. What we're going to learn today is we are going to figure out how we can go backwards. So partial fraction decomposition is the process of writing a rational expression that would be like some polynomial divided by a different polynomial as a sum or difference. So like a polynomial divided by another polynomial plus or minus a completely different polynomial. Okay, so basically you're going to start with the end here. So we'll be given something like this, and the question is going to be, how can I work backwards to make it look like that? So we're going to go in reverse process here. The reason you're learning how to do this is because there are some situations in calculus where you're integrating a function, and it's more useful to write it as its sum or difference, as what we call, these are partial fractions. So it's more useful to write them as partial fractions than it is as the whole rational expression. Okay, so this will be very useful in calculus, and you'll understand why when you get there. Okay, I just want to note that it's important that the two polynomials have no common factors other than 1 or negative 1, because everything is a factor of 1 and negative 1. And the reason this is because let's say p of x is, I don't know, like x plus 2 times x minus 1, right? That's a polynomial. I just put it in its factored form. And let's say q of x is x plus 2 over x plus 3. If you divide those and they have a common factor, they'll cancel out, and that won't be in its simplest form until it's canceled. So we want to make sure it's simplified, is basically what that's saying, so nothing cancels out. We'll do the partial fraction decomposition once we get it in its simplified form. There are two cases that we're going to talk about for today. One is where the degree in the numerator is less than the degree of the denominator. So the degree here is a square, the degree here is 1. So the degree would be less in the numerator than the denominator. And then we'll do the reverse case when the degree in the numerator is higher. I hope you're all thinking to yourself, this case 1 example looks oddly familiar, doesn't it? Oh yeah, it was the answer to our problem up here. So we're going to break this polynomial up into its parts. I already know that the answer broken up is going to look like this. And sometimes I think it's helpful to know the answer to learn the process. So by the end of our whole process, I should get the final answer, 3 over x plus 2 plus negative 2 over 2x minus 3. Okay, so I already have my answer. I'm done, right? No, because we don't know how to get it if we didn't already know the answer, and that's what we're going to learn today. Okay, but I can use this to kind of determine some steps to take to solve this problem. So I know when I'm breaking this up into partial fractions, I'm going to have to either add or subtract two rational expressions together. Now, if you look at our answer here, I'm just going to make it a plus sign, because if the numbers are negative, then it'll take care of itself later. But I know the denominators of my two partial fractions are just the linear factors of this quadratic. So the first thing you always want to do is you want to factor the denominator so you can figure out what the denominators of the partial fractions are. So if you don't believe me, go ahead and factor this polynomial. But you should get x plus 2 times 2x minus 3. X times 2x gives me 2x squared. Outers and inners give me x. 2 times negative 3 gives me negative 6. Okay, so these denominators are just the linear factors of this polynomial here. So I'm going to always start by factoring it and then writing my two partial fractions so the denominators are those factors. That's step 1. Okay, so 4x minus 13 over 2x squared plus x minus 6 will break down into this form. Now the one thing I don't know is where this 3 and this negative 2 came from. Like I can see where these came from, not sure where those came from. You can't just guess them. So we need a placeholder for that 3 and that negative 2. So I'm going to call this one A. for a placeholder, and I'm going to call this one B. I don't know what A and B are. That's what I need to find. Okay, so if you think about this, I want these two sides to be equal. So I want my numerators to all be the same and my denominators to all be the same, and then the whole fractions themselves will be the same. And fortunately, our denominators are already exactly the same. Like if I add these two things together, I'll get this. Okay, and you can kind of see that if I rewrite this right-hand side here as one fraction. So to do that, let's combine like terms, right? Let's multiply this by 2x minus 3, and this by 2x minus 3, and x plus 2, and x plus 2. So basically what I'm saying is let's combine this fraction into one fraction. So you have a times 2x minus 3 plus b times x plus 2 all over x plus 2 times 2x minus 3, which would be our common denominator. And this should say 13, shouldn't it? 4x minus 13. Okay, so 4x minus 13 over our polynomial 2x squared plus x minus 6. And all I've done is add these together by creating common denominator would equal this. And like I said before, these denominators are equal. And you can see that once I've added them. So if the denominators are equal, all that needs to happen now is that our numerators are equal, and then the whole rational expression will be equal. So we can kind of just ignore the denominators for a second. And it's not like it's going away. I just need to focus on making the numerators the same, since the denominators already are. So I can just focus on this equation and figure out what values I would need for a, b, and x to make these equivalent. Now this is a three-variable equation, which is how it ties into this unit. But luckily, I know I said before you need three equations to solve three variables. In this case, you do not need three equations. Instead of that, we just need to substitute something in for x, and then we can isolate a and b. But that's still a two-variable equation, so if I can pick something strategic to plug in for x that will also eliminate a or b, then I can solve this. So the only way I'd eliminate b, for example, is if I plugged in something for x that made this b times 0. Because b times 0, that would just go away. So what would I have to plug in for x to make that happen? Well, when is x plus 2 equal to 0? X would have to be negative 2. So if I can plug in negative 2 for all of my x values here, I'm going to eliminate the x because I plugged something in for it, and I'm also going to eliminate the b. So let's go ahead and do that. I'd have 4 times negative 2 minus 13 equals a, and I'm going to plug in negative 2 for x. So it'd be 2 times negative 2 minus 3 plus b times negative 2 plus 2. But that would just be b times 0, which would cancel out my b. So now I have only one variable and I can solve for a. Now the reason I can just pick something to solve for x is because this equation here is true for any x value I plug in. As long as you plug in the same x value, you can plug in whatever you want. And now I can solve for a by just kind of evaluating this up. So 4 times 2 is negative 8, minus 13 is negative 21, equals a times, this gives me negative 4 minus 3, which is negative 7a. Divide both sides by negative 7, you get a is 3. Okay. Now I have a value for a, I also need to do this to find b. So in order to find b, I'd have to cancel out x, and I'd have to cancel out a. So in order to do this, I want to plug in whatever is going to make the a number here 0. So what would I have to plug in to make this 0? Well, when is 2x minus 3 equal to 0? X would have to be 3 halves. So I'm going to plug in x equals 3 halves for all my x's, and that should also eliminate my a so I can solve for b. I'm going to have you try that on your own up here, and I'll come back with the answer. Okay, so if I plug in 3 halves for x, that will also cancel out my a. I'll have 0 a's, so I don't even need to write that. And I actually get b is negative 2 once I solve, and you're going to have to do some fraction work there. So the point of this is now I found the numbers that go on top of the partial fractions, right? So like I can break this down, and I get a is 3, so it'd be 3 over x plus 2, which is what we wanted, and b is negative 2. So negative 2 over 2x minus 3, again, is what we wanted because we already had our answer from the first problem. So that is how you would break down a rational expression into its partial fractions. Now case 2 is a little bit different because the degree in the numerator is greater. The degree here is a 3, whereas the denominator's degree is a 2. Basically what you want to do here is you want to make it look like case 1. So in order to make it look like case 1, we're going to have to make the degree in the numerator less. The only way to decrease the degree in the numerator is to divide these two by each other. So you're going to have to take 3x squared minus 2x minus 1 and divide it into our polynomial. So basically you're going to do what sign you see there. If this says divide, you're actually going to divide. And I'm just going to recap this process since it's been a while. So you're going to focus on the first terms, and you're going to say how many times is 3x squared going to 6x cubed? Okay, I'd have to multiply 3x squared by 2x to give me 6x cubed. Now you're going to distribute that. So 2x times 3x squared gives me 6x cubed. 2x times minus 2x gives me minus 4x squared. And 2x times negative 1 will give me minus 2x. Okay, then you're going to go ahead and subtract. So these should cancel. That's what you wanted. You subtract a negative. That's really like adding. So this is going to be 9x squared. Okay, you don't have any x's to combine this with. So it's really like 0 x's minus 2 x's. So it'll leave as, or excuse me, minus a negative will be plus 2x. So I have 0 x's minus negative 2 x's plus 2x. And then the 7, it's really like 0 constant number. So negative 7 minus 0 will still stay as negative 7. Now you're going to repeat this process. How many times is 3x squared going to 9x squared? And the answer would be plus 3. And you're going to repeat that. Distribute that plus 3 out to all three things. So get 9x squared minus 6x minus 3. Then you're going to go ahead and subtract those. So these should cancel out like you wanted. Subtracting negative, that's like adding, so you get 8 x's. Subtract a negative, it's like adding again, so you would get minus 4. And you can't put 3x squared into 8x, so that's as far as you can go. This would be the remainder. Okay, so the key is now I want to rewrite this. Okay, so this is what divided in evenly, so that got divided in. So I would rewrite this as 2x plus 3 is what divided in evenly. And you always add on the remainder, and this is a review from the previous unit. But my remainder I would write as 8x minus 4 over what we were dividing in. So that's 3x squared minus 2x minus 1. Okay, now this is already written, you know, as a partial fraction. Like that's as simple as it gets. We can't break that down because it's not a rational expression. So for the time being, we can kind of ignore this and replace at the end. This is what we want to break down into partial fractions because this is a rational expression that needs to be written as a sum or difference. And now the degree in the numerator is less than the degree in the denominator, so we could just repeat the process from case 1. And I'm going to leave this for you to try. I want you to break this down into what its partial fractions are using the steps we talked about in case 1. So this is your on your own problem for today. The only difference is at the end, you'll rewrite it as a sum, but you'll have to add this 2x plus 3 on because that was also part of the original problem. We just divided it out to make it look like case 1. So you do have to remember quite a bit of background knowledge. You have to remember long division. You have to remember what rational expressions are and how you combine them, or at least it helps you understand it. But the goal of this is it's going to help you integrate functions in calculus. Okay, so we're building this skill now. If you have any questions about the skill, please come in and ask.